So we had quite a lot of interesting talks and discussion today about a number of topics, key topics in quantum gravity, from unitarity to stability, positively bounds, and so on, and the Saturn's the approach of GIA. So I would suggest that we start with some additional questions to the speakers of the second session, and then we can smoothly move to a more general topic, and in particular unitarity and causality in quantum gravity. But let's start first with questions, additional questions to the speakers. And so I see that there is a question by Alessandro, but first, Anupam, I think. So, Gia, you say that you didn't understand one of the questions of Anupam.
Anupam
Yeah,
had
so
this
I think in general what Gia says, I agree with. The point which I was making is that this Grossman, the amplitude in the string theory, it is always UV finite. So string theory must have a mechanism, something like what
why does it contradict?
You must know how to ameliorate the UV problem.
No, but why does that contradict to what I'm saying?
No, that's what I'm saying. It doesn't contradict. So I'm saying that there must be a similar interpretation one can find in your formalism of classicalization.
Well, we did a fully fledged string computation. This amplitude 2 to n is a stringy computation. We did both. We did, as I said, we did in quantum effective theory of quantum gravity, low energy, and we did in string theory, and the results are the same up to 1 over n. So
I agree.
There is
language, you have a torus with n insertion, and you would see that there is some suppression in the UV amplitude. So you would not form. UV is ameliorated somehow.
Well, there is this general property of string theory that it starts softening. So if you are in a weakly coupled string theory, what happens is that string modes in weakly coupled string theory, string scale is lower than the Planck scale, and so what happens is that string modes start entering in the domain in which quantum gravity would still be weakly interacting. So they just take over in that domain. And in that domain, there is you are in weak string coupling, and the amplitude 2 to 2 amplitude has absolutely no problem with unitarity or anything. So everything is fine. So that's just a fact of string theory. So here, what we are interested in, the ultra Planckian center of mass energy. And what we are observing is that the behavior of those amplitudes in string theory or in low energy quantum gravity is the same. And we always unitarize by producing soft multi-graviton states with the surprising matching with black hole entropy. So that's the fact that we're observing. So yeah.
Okay, Alessandro.
I have a comment which is a criticism of talks by both Salvio and Mannheim. Basically, it's the same point. So maybe let me start now from Alberto Salvio. He said that the classical theory with negative kinetic energy is metastable enough. So we studied the theory with a few degrees of freedom, for example, 2. And then indeed we find that the runaway time for the Ostrogradsky instability is exponentially suppressed because of something Kolmogorov, something difficult, it's true. But when instead you go to classical field theory with infinite number of degrees of freedom, the runaway is not exponentially suppressed. The time of the instability is the time typical of any Boltzmann equation, which means proportional to coupling squared. So you compute its rate, and it's 1 over m Planck squared, which is good enough because in cosmology the Hubble rate is 1 over m Planck to power 1, and that's why it's slow enough. So the rate is not suppressed, but it's slow enough just because gravity is weakly coupled.
Yeah.
So here, now having infinite degrees of freedom gives the result completely different from having 2 degrees of freedom. And
Yes.
this is also the problem that I see in the talk by Mannheim. Now, he basically computed the 2 degrees of freedom, M1, M2. And now what one would really need to show is that the same good happens in field theory. And the problem in field theory is that there are infinite number of states. So for sure you have degenerate states, which is just trivially what we call decay and scatterings in particle physics. And the degenerate states, give it's like having M1 equal M2. You get this divergence, a mess happens. So a much more difficult computation is needed to know if the final result is good or bad. Now, as far as I understand, we don't know if this kind of theory can make sense or not at the end. One needs to compute more.
So can I answer?
Yes, of course.
So I agree that you need to have a small coupling of the graviton. So if the coupling is over 1, then as soon as you excite the graviton, you excite also the instabilities. So regarding your comment about quadratic gravity, you need to have a small coupling. Otherwise, you get immediately instabilities. So I don't see a contradiction with what you said.
Oh, there is no exponential suppression of the metastability time. It's just what you get trivially from Boltzmann equation. It's
But
just
you said
that gravity is weakly coupled, and then it's typical that in cosmology you never care about the gravitational scatterings because they are so weak. It's just this.
But at the end, you said that you agree that the metastable time is long enough for the small
but
coupling.
the proof done with 2 degrees of freedom does not apply to field theory with infinite degrees of freedom. And that's the problem now that I see in both talks.
But at the end, you said that if you consider quadratic gravity, if it has a small enough coupling, then the metastable time is long enough.
Yes.
No, that isn't what you're saying, is it? You're saying that with an infinite number of degrees of freedom, the coupling, the decay time is 0, right?
Right, it's 0, right. That is, I mean, I think I understood correctly the comment, and I think I fully agree with that, because the issue in quantum field theory is that we have to integrate over infinite number of degrees of freedom, and that's where the problem is hiding. And so, yeah.
No, but
A lot of people have calculated this. It became
calculation by Alessandro. Alessandro, do I understand correctly that you said that if the coupling of the ghost is small enough in quadratic gravity, then you get metastability time, which is large enough?
So this is not an issue about the classical theory.
Yeah, about the classical theory. I'm not talking about the quantum theory. The classical theory. I'm talking about the classical theory, yes.
So here is one specific example where you see the difference between 2 degrees of freedom
and infinite. Yeah, it's
qualitatively different. And I'm telling the same issue applies now to the attempts of making sense of this theory, for example, like what Mannheim proposed.
In the case of Mannheim, I don't see a discussion about field theory at all. So it's just 1 degree of freedom.
Yes, he does now these rotations in a system with 2 degrees of freedom. Okay, it works. But what we need is quantum field theory where having infinite degrees of freedom make the computation much more dangerous.
Yes, this I agree with you. But,
if I can
well, he's not claiming that the classical theory is stable. That was the very surprising thing about your claim. He's claiming that if you took the h bar goes to 0 limit of his theory, you'd get something else. It's not clear what you'd get, but you certainly wouldn't get quadratic local R-squared gravity.
I am mixing 2 different points, and the common point is that 2 degrees of freedom is not quantum field theory. So
Okay.
if you show that something is good with 2 degrees of freedom, it's not
Can
enough.
can I comment?
Okay,
on this?
yes, so Philip.
Yes, okay. I went through the non-relativistic Pace-Uhlenbeck example just to show you the general ingredients. But I've also worked through the original theory with the d mu d nu phi, d mu d nu phi. I've worked the whole thing out, and it's a regular quantum field theory, and you find that the operators are not Hermitian, and you have to go off the real axis, and that's what I'm claiming. But once you've done that, you've got an infinite dimensional Hilbert space. And now if you want to do perturbation theory, nothing can go wrong in that space because you can't change the signature of a Hilbert space in perturbation theory. Now you asked another question. I had 1 over k squared minus m1 squared minus 1 over k squared minus m2 squared. You asked me what happens if m1 squared equals m2 squared? And that's a whole, that's an even longer story than the one I presented today, because if you write 1 over k to the 4 itself, pure 4th order, then you can write it as the limit 1 over m squared of 1 over k squared minus 1 over k squared plus m squared. But you have to take the limit m squared goes to 0. And that limit is singular because you can't make the decomposition, the partial fraction decomposition, if the mass is 0. And I didn't spend any time on this, but if you remember, I introduced that similarity transformation that got me to the harmonic oscillator. That similarity transformation is singular if the frequencies of the 2 modes are the same. And so the pure 4th order theory is, the discussion is completely different from 2nd plus 4th. So all I talked about today was how to handle the ghost problem in 2nd plus 4th. The question of how to handle the ghost in pure 4th is a completely different discussion. The theory is unitary, but in a very unusual way, because the Hamiltonian, you could have guessed, if the transformation is singular, you can't diagonalize the Hamiltonian. And it turns out to be a Jordan block Hamiltonian. Yes, and Carl Bender and I have written a huge paper on how to have unitarity in a non-diagonalizable theory.
Sorry, just clarify now. I worry about this M1 equal M2.
Yes.
Because when you do quantum field theory, you get an infinite set of like this, omega 1 equal omega 2. There is infinite set of degenerate states. And that's why you need to compute much more.
Yes, but what I was saying was that setting M1 equals M2 is not the correct way of looking at the propagator. 1 over k to the 4 has an outside it a 1 over m1 squared minus m2 squared. And if you let m1 equal m2, then that factor becomes infinite. And therefore, the partial fraction decomposition isn't valid. And whatever you want to say about the partial fraction is irrelevant for the pure 1 over k to the 4. You have to start that theory all on its own. Now, if you remember a moment ago, I mentioned to Terry Tomboulis that in PT theories, you can have a region where the energies are real, and you can have a region where the energies are in a complex pair. But there's a transition. And what happens at the transition is the complex pair of energies have complex conjugate wave functions. And when you go to the limit, the 2 wave functions become the same wave function. And that means the Hamiltonian is no longer diagonalizable. It doesn't have a complete set of eigenstates. And so the whole discussion of 1 over k to the 4 is a discussion of how do you handle a Hamiltonian whose set of eigenstates is not complete. And that's, I mean, I can tell you exactly how that works, but that's a whole different problem. You can't infer anything, I'm sorry, you can't infer anything about a theory where M1 is not equal to M2 as to what you might know about when M1 is equal to M2, because the limit is singular.
Sorry, just now to be clear now, I am telling you, when you do quantum field theory,
yes,
you end up to dealing with an infinite set of these degenerate cases. So you expand around one dangerous point, you have to see if you now go up or down, good or bad, and this has not been done.
I'm afraid I didn't follow what you just said. Please repeat.
Sorry, I'm telling M1 equal M2. For me, is just a mathematical way of telling that when you do quantum field theory, you get an infinite set of degenerate states, and that's why you get the same degenerate problem.
No, but what I was trying to tell you was that the Hamiltonian stops being diagonalizable. The states are in the Hilbert space. That doesn't change, but they're no longer eigenstates of the Hamiltonian. That's the thing that changes, and that's why that's how the theory makes sense. But the completeness is the completeness of the Hilbert space, not the completeness of the Hamiltonian. Now, it's very unusual that the eigenspectrum of a Hamiltonian would be smaller than the eigenspectrum of the entire Hilbert space. But that's exactly what happens in the 1/k to the 4 theory.
So I am just telling that in quantum field theory, you end up having to deal with this case to know if the theory is good or bad.
Yes, but they're not. I'm just saying they're just not eigenstates. That's all. The states, of course, the states are in the Hilbert space. Yes, but they're not eigenstates.
You have now to diagonalize a set of infinite degenerate states, and this computation has not yet been done.
I'm sorry. You can't diagonalize the Hamiltonian. That's what I was saying. It's non-diagonalizable. It's a Jordan block.
Yes. So okay, you have to do the same you did now with 2 degrees of freedom, having an infinite number of degrees of freedom, and then necessarily you have degenerate states, and you have to deal with the most difficult case.
Sure, I'm not disputing. I'm just claiming that Carl Bender and I have precisely done that. That's all.
Maybe I could a little bit reiterate what Alessandro is asking. Hi, Philip. Hi. So let's take a simple case of the standard ghost problem, right, in quantum field theory. Right? Why we say that there is a problem when we have a negative energy particle? Because we can produce a negative and positive energy particles, and then by Lorentz boosting, we have infinite phase space. And so this is an example of this infinite degeneracy of quantum field theory. And this is the problem, and this what has to be demonstrated. What cures it in this incarnation?
Oh well, what I said was that you have a realization that looks like it has negative energies, and another realization that looks like it has negative norms, but they're different Hilbert spaces. And so
let's pick one of those.
There's no Hilbert space where you have both. You don't have.
Let's pick one. Let's pick up one description.
Okay, so I constructed the Hilbert space for which the Hamiltonian has well-defined boundary conditions at infinity. And what I discovered was that all the states in the spectrum had positive energy, and all the states in the spectrum had positive norm.
Yeah, and if that's what you can prove, that all the states have positive energy.
Yes, we solve the theory analytically. Yes.
And no degeneracy.
I'm not sure what you mean.
And an acceptable classical theory. Let's not forget that.
I certainly will forget that, Richard. We live in a quantum mechanical world. There is no limit in which you can let h bar go to 0 because h bar is not 0.
That would be acceptable for some other theory than gravity. The only low energy data we have for gravity is classical. If you just define an arbitrary theory as quantum gravity, you're throwing the baby out with the bathwater.
I don't want to get into the discussion with you about what kind of classical gravity theories we should anticipate. What I'm saying is that you have to take care of the quantum theory, and the classical limit is not the h bar goes to 0 limit. It is the limit of macroscopic occupation of quantum operators. And whatever they obey, they obey. And there is no h bar goes to 0. That was an accidental discovery on the road to Heisenberg's development of quantum theory. But h bar never goes to 0. The
Well, I
classical,
mean,
the
no,
classical limit is not, it is nothing to do with the classical theory that you wrote down and tried to quantize. That's
no, Philip,
That's the problem.
That's not a problem. It's just not required by reality. I mean, reality
And
is.
you get the tides. Getting the tides right is required by reality.
Oh, now you're asking a different question. You're asking me whether the theory I've described will fit classical observations, and of course the answer is yes. And I've worked all that through. But I get two big bonuses that you don't have. One is I don't need dark matter, and the other is I do have a solution to the cosmological constant problem because of the conformal symmetry. So, I mean, if you want to promote Einstein gravity, which you're free to do, you have to solve the dark matter problem and you have to solve the dark energy problem. And until you do that, you can't claim that you've got a consistent classical theory, never mind quantum theory. Without a solution to the cosmological constant problem.
no, but here we're discussing
standard gravity is not, has to be regarded as a step, but not as the answer.
But this is a different question. I mean, here we're asking about consistency. So there is a question of consistency and consistent classical limit.
I have described. I'm claiming that. I'm claiming that that's all there. Yes.
No, if you have
what Richard's unhappy with is that I don't have his classical limit.
No, but that's a separate question.
That's a different.
I just want to see what the dynamical variable is and what the field equations are.
It's the metric. Yeah, I mean, it's just the metric.
And it's a local metric-based theory?
Yes, of course, it's C-squared action.
Well, but that's not the theory. That theory has negative energies. That theory is unstable.
I just gave you the proof that it doesn't. All right, Richard, give me the proof that it does.
Well, you didn't give me the proof that it
I did. I showed you.
You said no. You said that when you quantize it, do all this other stuff, which you've admitted throws away the classical limit.
No,
that you get something that doesn't have negative energies. Maybe that's true. Maybe that's not. My question is, what is the classical limit of the theory that you get?
I just gave it to you. What you're thinking of is that the operators have to be real. They don't have to be real. They have to have eigenvalues that are real. And that's the point that Carl and I are making.
The classical metric theory is real.
Of course.
I mean, can maybe another question.
At this point, I think that Robert has a comment on this.
Robert had a question about instantons.
Yes.
I don't know if he still has that question, but I mean, I can answer that if he.
Yes, but I don't want to divert the discussion. So
no, just go ahead.
Okay, so this is now a question to, so I didn't understand the QCD analogy because so my question was, how do these QCD saturons look like? They should be Minkowski type configurations, but the instanton is a Euclidean configuration. So this is what I was confused about.
Yeah, no, that's a good point. It's a good question. So actually, the saturons can be both Minkowski type configurations and also Euclidean type configurations. Because the bound that emerges from unitarity is 1/alpha, and it doesn't involve energy. This bound is well defined. This entropy bound is well defined also for instantons. So there is a well-defined way, and the instanton has an entropy bound. It's again degeneracy of the instanton action. So if you simply count the number of microprocesses, you can think of instanton as a process, right? So it's not a Minkowski object; it's a process. So and now it's a macro process which consists of many possible microprocesses, because there is the moduli space of the instanton. So once you quantize the moduli space of instanton, you get a finite number of processes, microprocesses, and you get log of that finite number is an entropy. Okay, and that's what enters in the magnification of the instanton processes if you have now a unitarity transition. So the first answer is that the instantons have well-defined entropy. since I'm not talking about Bekenstein bound, by the way, I want to make it very, very clear that I'm not using Bekenstein bound. What I'm saying is that what I'm observing is that from unitarity, there is a different bound emerging, which is inverse alpha, 1 over alpha bound, which in certain sense is more stringent. Is more stringent, and also it doesn't involve the concept of energy. You don't need energy for that bound to define. So yeah, instantons saturate. And actually, so now what happens is that also in QCD you also can have saturons which are Euclidean states. This is what I discussed in the gluon process. So in 2-to-n scattering of gluons, you create a gluon lamp, and this gluon lamp has entropy because it has huge degeneracy with respect to the color, and that's the saturon for in a pure glue. So in a pure glue, there is the state, saturated state of gluons, and that's the saturon in pure glue. So yeah, these are the two states. Now, what is interesting is that both of those objects, instanton on one hand, and pure glue saturon, they saturate bound exactly at the confinement scale. So this is somehow how theory tells you that there is a correlation between saturation of unitarity by the scattering amplitudes and confinement. Okay, somehow theory decides to confine around that scale to prevent violation of unitarity for the further growth of the entropy. So this is the outcome. Okay, so does this answer your question?
Yeah, I think so. So you have two possible saturon states in QCD.
Oh yeah, even more. No, it depends on the theory. For example, if you have QCD with fermions, you can also have saturon states constructed out of baryons, because they can be very high representation of the flavor group. So for example, there you can have, for instance, you can have saturons which are skyrmion type also. Here I was considering pure glue. So in pure glue, there is a correlate. There are two states, two saturon states. One is gluon lamp, and there is a correlation with the instanton, and both saturate this bound at the same scale. At the same scale, yeah.
So if you shoot a huge number of gluons together with the total
well, you don't need
momentums,
to huge number. 2 gluons are enough because the 2 go into n,
okay.
And because this n gluon state has a maximal entropy, you are producing that with probability 1. So it's a 2 gluon scattering. It's just very similar to 2 graviton scattering. So in 2 graviton scattering, you are producing a black hole because that has a maximal entropy compatible with this bound, 1 over alpha. And in 2 gluon scattering, you are producing a gluonic saturon because that's the one that has maximal entropy. And that happens around the confinement scale. That's what we observe. That's what I observed, that it happens at the confinement scale. Yeah.
Okay, thanks.
Yeah, related to this question, if I may ask, so what would happen with the fermions and the Pauli blocking? You
mean if I consider scattering process of gluons into fermions, let's say fermion anti-fermion pairs? Yeah. So with fermions, the story is slightly different, but think in the following way. So the baryons are made out of quarks, and quarks are fermions. But you know that there is an alternative description in large N by Skirm, this idea of Skirm that was then very nicely clarified by Witten in series of papers. So in which you can describe baryon as a soliton of pions without any reference to fermions. So what happens is that effectively in baryons, fermions bosonize. And so you can describe it in that language. So then it works in a very similar way. But in general, it's true. You have to take into account fermion numbers.
Bob has a question or comment?
Yeah, you just said saturons occur around the QCD scale. Do you mean that they're produced at that energy and not much larger energy?
Yeah, so what I'm observing is the following, that when I'm computing 2 gluon into n gluon scattering cross-section, what happens is this, that cross-section is suppressed by this exponent minus 1 over alpha suppressed and enhanced by entropy of the gluon state. Now that entropy is given by the color of gluons. So this entropy is given by the color, by the number of gluons in the final state and the color. So little n, big N. Now you can recast this in terms of Toft coupling. And so what you see is that the unitarity is saturated for a critical value of the Toft coupling, order 1. Okay, to be more precise, like 0.54 or something like that. So that's what I'm observing. So I see that if I compute this type of cross section, that cross section saturates unitarity for the Toft coupling of order 1. Now, on the other hand, I know that QCD confines around that scale. That's sort of a independent knowledge. And what I'm saying is that there is an interesting observation that confinement scale somehow is correlated with the saturation of unitarity by the saturon state in gluon sector. So that's the observation, okay? Of course, I'm not explaining how confinement happens. That I don't know, that's a highly, but I see a clear correlation at the confinement scale. So the saturon in QCD emerges right at the confinement scale. Okay, and
you're not saying anything about what should happen at the LHC.
Well, at the LHC, you mean if you have some beyond the standard model physics theory with saturons?
Energy is much beyond the QCD scale. You're not saying anything about what happens there.
I know energy is so okay. Of course, real QCD has only 3 colors, and so in real QCD at very high energies, at LHC energies, theory has no saturons. So there we can at really ultra high energies we can forget about saturons for real QCD. However, if you have some new theory beyond the standard model theory, which is QCD-like or which has many degrees of many species, then you can have saturon in those theories, and then you can have very interesting signals for LHC in this type of theories, because saturons have very interesting signatures, experimental signatures, very well-defined spectrum, and very clear signal how they decay, how they, yeah. So right. Unfortunately, with real QCD at LHC energies is too high. So yeah, there are no saturons.
But for gravity, you're saying it's very different, that for energies much above the Planck scale, you really will produce these saturons.
Exactly. So gravity is sort of an upside down story with QCD. So somehow QCD, so gravitational Toft coupling hits 1 at high energies, and the QCD Toft coupling hits 1 at small energies, at low energies. And so that's the difference. So basically, the entropy of the saturon is governed by this effective collective coupling, which is alpha times n. And the question is, where does this alpha times n saturates 1? So when it becomes order 1. And so for gravity, that happens in ultraviolet. And also gravity has, of course, this advantage that gravity has saturon for arbitrarily high energy, because we have arbitrarily high mass black holes. In QCD, we don't have continuum spectrum of saturons. We only have saturon at 1 energy scale, and that's it. So that's the difference, yeah.
Okay, now there is a comment or question by Tombulis.
Yes, can you comment how this picture would apply to a theory, let's say a generic gauge theory, maybe, you know, with several Higgs fields that has several phases, including maybe complementarity, continuous phases between Higgs and confinement, and a massless phase. So as you change phases, in other words, how would the saturation picture change? Can you describe that?
Yeah, that's a very interesting question. Actually, I'm also interested myself in that picture. In other words, so in theories with Higgs bosons, it differs from pure glue, because we can have, in principle, we can have several energies at which saturation happens. Okay. Mm-hmm. So, for example, yeah, because of the obvious reason, because you can, for instance, at low energies theory can be in the Higgs phase, but then at very high energies, part of this theory, the effective number of massless gluons can grow because you're. So yes, I mean, if you allow theory to have Higgs multiplets, so that it's Higgs on some different energy scales, in principle, you can have regimes in which you have 1 saturation point, so you produce 1 saturon at some given energy, and then with some gap at different energy scale, you produce another saturon. Very interesting question is, and now, for example, I'm trying now to understand what's happening. If theory has a conformal window, okay, so that theory if theory has a conformal window that allows to have a fixed point,
Yes.
where the Toft coupling freezes effectively, so where alpha n is basically Toft coupling that doesn't run. So
Right.
that theory behaves sort of like gravity from the point of view of black holes. And so the question is, if we have a theory with in some kind of conformal window or at a conformal fixed point, whether this theory can produce a continuum spectrum of Saturons. For instance, that's what is an open question. Yeah. Now, unfortunately, understanding of theory within conformal window is not so good. And okay, I mean, the knowledge is there in that window is limited. So it's yeah. So therefore, we have to somehow yeah, we need some additional information input there. But it's an absolutely valid question what you're asking.
Shravan?
Yeah, well, a very short question to give. So, naive question. So, why you are only talking about 2-to-n scattering? I mean, what is really special about it? I mean, you can also talk about m-to-n scattering and many particle scattering.
Sure.
Yeah.
Yes, thanks. So no, I'm talking about 2-to-n scattering because that's an extreme classicalization. Because I mean, if you want to have really scattering experiment, you need at least 2 particles. I mean, you cannot have any. You cannot have scattering experiment with less than 2 particles. And so this process of saturation is a process when you have initial state, which is quantum in a very good approximation, and then it transits into a state which is classical in very good approximation. Okay, so for example, you have E plus E minus of solar mass energy. E plus E minus is an absolutely quantum state, but then it produces a black hole which is solar mass, and that state is classical in a very good approximation. So that's the only reason. So to sort of make the effect sharper. Of course, classicalization becomes easier and easier if you have more initial number of particles. With high number of particles, it becomes less and less difficult, right? So if you are, for instance, you know that if you are in some kind of thermal, if you have at high temperature, for example, we can produce even sphalerons, even in weakly coupled theory, without any saturation. So at some point, if number of initial quanta is very high, you no longer even need saturation. You can just simply produce those. Okay. I mean, there is an interesting connection. There may be some interesting correction with colored glass condensate in QCD. So actually, Raju Vanagopalan and I, we are sort of trying to understand this connection. In QCD, there is this state so-called colored glass condensate, and yeah.
I think Alberto has a comment.
Yes, I was answering a question by Andrei Barvisky, asking me about the probabilistic structure of the quantum theory, and just said that the argument with the frequency operator showed that the indefinite metric is not the one that has to be used in the Born rule, but you have to use another norm, which is positively defined. And then you get positive probabilities that sum up to 1. This was the comment.
Sorry, and this has the same problem as in the talk by Mannheim. We don't know if it works in quantum field theory.
Well, I know. I mean, if I can just make a few comments.
Yes.
Going back to what Gia asked a moment ago, Carl Bender and I have proven, we've constructed the Hilbert space, and we've shown, it's a proof. It's not a claim, it's a proof that all the states in the spectrum have positive energy and all the states in the spectrum have positive norm. And there's an infinite number of them. And we've done this for a quantum field theory. And I showed you in my talk the two-body to two-body scattering, the one loop. And I showed you how unitarity is obeyed, even though you have contributions which have a negative discontinuity, and they're just they're cancelled by other contributions that make the full scattering amplitude unitary. Going back to, I also want to comment to Richard, classical does not mean real fields. Classical means C number, namely quantities that commute with each other. Now, I mentioned that you can continue into the complex plane, and you can apply similarity transformations in the quantum theory and symplectic transformations in the classical theory, and they leave commutators and Poisson brackets invariant. Now, I also mentioned that the metric would be pure imaginary, and you objected to that. But the point is that the metric appears, the covariant always appears with a contravariant. So it's the G mu nu upper times the G mu sigma lower, which is delta mu sigma. Now, you can't, I'm not going to change the delta has to be 1, but the contravariant is always the inverse of the covariant. And the connection always contains equal numbers of contravariant and covariant metrics. So does the Riemann tensor. So we never actually have measured in physics.
What about the length interval?
The length interval does not appear anywhere in any Lagrangian. I'll come back to that in a moment. That's a question of how you get geodesic behavior. But please,
Philip, just a small question. So
I haven't finished.
No, you joined two completely different topics, and can we maybe go step by step? First, clarify first the first thing.
Oh, okay. So
because you jumped to the other topic, which is I mean, of course I agree, both are important. I'm sorry to interrupt you, but
sure, go ahead.
But regarding the finiteness of the regarding the infinite degeneracy, here's what I was trying to say. So in quantum field theory, imagine for a moment that we have some quantum field theory in which I can have a negative energy particle. Okay,
yes.
For a moment. Now, nevertheless, I can say that energy is conserved, and so I'm looking for a process in which I have some initial state of positive energy decaying. So by default, I'm only looking at in the Hilbert space to the states which have positive energy. So all these states have positive energy, norms are finite, but nevertheless, I have infinite degeneracy, which in the standard quantum field theory would make phase space infinite. And so the lifetime of that positive energy state would be 0, because it can decay into a pair of positive energy particle and negative energy particle, and then by boosting, you have infinite degeneracy. And this is the problem. So the problem is with infinite degeneracy, not only with the positivity of the energy.
Well, first of all, I don't have any negative energy states. There are none in the Hilbert space.
I gave you example.
This problem doesn't exist.
But I just gave you example when I said
this example doesn't apply to the case I discussed.
No, because I said you can have a negative energy particle, but you can restrict your state to have positive energy, because you can always
I haven't done that. I've not got any negative.
No, I am giving you an example to. No, I am doing that. I'm giving you an example that illustrates the problem. I'm trying to give you an example that clearly illustrates the problem while all the energies are positive. Because there is degeneracy. In other words, there are two problems. One, the negative energy is one thing, but even if your energy is positive, you restrict your Hilbert space to positive energy densities or to positive energies only. If the degeneracy is infinite, you have to worry about it. I think this was the question, Alejandro's question, but maybe in any case, I mean, this is my question. My worry would be that when you have infinite degeneracies, you have to make sure that the rates are finite.
Well, I've constructed the entire Hilbert space. I mean, what are you saying that's different from any other quantum field theory? I mean, why would it not just occur in lambda 5-4?
Because in lambda 5-4 you don't have infinite degeneracy, because there is a finite phase space, precisely because the particles only have positive energies, despite the fact that total energy is positive.
I have the same situation. All my particles do have.
Well, if you have same situation, sure. That's what I wanted to say. But usually that's what. I mean, usually that's the problem with ghost-like They give you infinite degeneracy.
I had misunderstood what you were asking me. I thought you were asking me about the theory I had, which only has positive energies. And you were telling me about a shortcoming of a theory which had negative energies as well, as an implication for what happens with the theory that only has positive energies. That's what I thought you were trying to say. But I think we're in agreement that there's nothing wrong.
Negative energies, not negative energies.
There's nothing wrong with the theory where all the energies are positive. I mean, it's just the standard Feynman contour.
No,
You
I
close
was trying
below,
to
and
say,
you close below, and all the poles are below the real axis, and they're all.
no, I was trying to say something completely different. I was trying to give an example. I was trying to say why theories with ghosts normally are a problem.
Ah, okay, good.
Because they give, not because you necessarily end up with negative energy state.
Yes.
The theories with ghosts are a problem because they give you infinite degeneracy. For
Yes,
example, vacuum can decay into a ghost and a normal particle, and when you integrate over phase space, that's infinite because of Lorentz boosts.
Yes, but what I was trying to say in my talk was the claim that there are either ghosts or states of negative norm or states of negative energy presupposes you're working in a very specific Hilbert space. And I work in a different Hilbert space. And in that Hilbert space, there are no negative norms and there are no negative energies.
No, I'm not making any claim. I'm just asking a question. No, okay, I'm not. I mean, I didn't check your calculations. I'm not saying anything. There is anything wrong there. I'm saying this is the potential worry that is immediately comes up when in this type of theories. That's what I was trying to say.
Okay, well, what I was trying to say in my talk, I understand what you're saying. What I was trying to say in my talk was that your whole assumption that there are negative norm states or negative energy states is because of invalid reasoning. You can't say that from looking at propagators. You've got to construct the Hilbert space first. And that's what Carl Bender and I did. And we came up with a very different outcome than the expectation. But the expectation is not a description of the theory. It's a description of a particular Hilbert space that you chose to work in. And if you go back, you'll find that in that Hilbert space, every single state is not normalizable. And that's why you don't work there. I mean, that was the point of the work that we've been doing. If I can.
Yeah, sorry, I interrupted this answer to.
No. That's fine. I mean, that's the idea behind the discussion. If I can go back to Richard, in gravity, the only quantity that's measured is the connection. And the connection contains covariant and contravariant metric, and you don't know the phase of the metric.
I don't accept that, Philip. What about?
First, Richard, sorry.
There's no other quantity. Richard, there's no other quantity in the
What about p squared? G mu nu, p mu, p nu.
Okay, I'm working with pure Riemann tensor-based theories. Okay, that's what I'm looking at.
Well, gravitons, last time I checked, could have momenta. What about p mu, p nu, g mu nu?
They're not in the action. The action contains geometric functions of the connection that are general coordinate scalars. That's
the action contains one net metric. That's why it matters whether you have the plus minus signature or the time-like signature, right? But the key issue is, what is your classical theory? Because it doesn't do any good to have. It doesn't do any good to have a quantum field. Let me make you've talked and talked and talked, and let me make just one little comment. It doesn't do any good to have a theory of quantum gravity that has positive energy and has positive norm if it doesn't explain the tides. I want to see what the classical theory is, and it's very peculiar what it's going to be. It can't be the R squared theory that you started with, because that theory certainly has negative energies. So, and in fact, it can't even be any metric theory.
The R squared theory does not have negative energies if you quantize it the way I showed.
Well, I talked about the classical theory. I want to see what the classical theory looks like.
Okay, let me
okay, so
I
think we are in a loophole where you don't understand each other. So I think.
Can I say a general question? Very general question. I mean, we have heard many solutions to the ghost problem. 4 solutions. I want to ask, well, I mean, also Philip. So the thing is, your solutions are valid for any theory. I mean, not only fourth order gravity, any classical theory which apparently have ghosts. Then it is. Then we don't have to worry about the ghost at all. We just can construct infinite number of theories. Which,
look, they're saying that in quantum mechanics, if you take V of x, one-dimensional quantum mechanics, if you take v of x is equal to minus x to the 4, no problem. It makes a perfectly good theory with positive energy.
You know, Richard, you're jumping ahead. Carl Bender has written papers with minus lambda 5 to the 4 where the energies are positive. They're not positive classically, but that's irrelevant to the quantum theory. But the answer to Shravan's question is, I'm not claiming that every fourth order theory can be treated this way. I can only claim that the ones that I've looked at. But we have suggested a technique for addressing other theories. I mean, in the end, all you have to do is you've got to get a Hamiltonian, you've got to construct a Schrödinger equation, and you've got to check whether the wave functions are normalizable. If the wave functions are normalizable, then you're dead. And then all of the issues that Richard has raised all come immediately. The only chance you have is if the wave functions are not normalizable. And then you've got.
Well, let's just stop right at that point. Let's just stop right at that point. The Ostrogradskian quantization of it with negative energies certainly has normalizable wave functions. I get to pick what they are, and they're negative.
Richard, I will make a statement which is a mathematical statement, and it's in my papers. When you write down the theory I worked on, the Pesulenbeck Hamiltonian, and you write down the Schrödinger equation and you solve it for positive energy or negative energy, you find non-normalizable wave functions. I'm stating this as a mathematical fact, which I've checked. And I'm not saying that this will happen in other theories.
Okay,
I'm just saying it will happen in the theory I'm interested in.
There is a question by Luca.
Okay, unmute yourself. Okay, thank you. Okay, yeah, so actually it's related to Philip and Richard, basically, discussion. So let's try to make something more clear. Okay, let me first confirm one thing, Philip. So the question to the answer to the question, which is your classical Lagrangian, is Weyl square, right? That's what you said. Okay, very good. Now, of course, we know that if we take Weyl square and we go at Hershey where we hit, for instance, the ghost instability, okay, the theory is not good, and that's where the problem is. Now I want to understand if the problem, is for you is not a problem, because you are saying that basically when we reach some energies, we cannot trust anymore our classical theory, okay, and so we need to quantize, and does not make any sense to take the classical limit. Is this your point of view?
No, it doesn't make any sense to take the regular classical limit. Perhaps I can state it to you in the language of path integrals. You write the path integral for the fourth order theory, and you will find that if the measure is real, the path integral does not exist. You have to continue the measure into the complex plane in order to get the path integral to actually exist and be a finite object. Then when you've done that, in the classical theory, it means that you've made a symplectic transformation on the operators that have taken you into the complex plane. And as I said in my talk, a thing that looked like minus z squared, which would be unbounded from below if z were real, becomes bounded because of the continuation from z to iz. And that's the same continuation that I have to make to enable the path integral to even exist.
Okay, so classically.
So I can say it the following. Classically, you can write down a classical action and you can write down a path integral. That path integral has to have a measure for which the integral exists. And Richard is absolutely correct. If you work on the real axis, you'll get negative energies. And if you go Euclidean, the action will go like e to the minus the lowest energy times tau. And if the lowest energy is negative, and you let tau go to infinity, the integral will blow up. That's the standard Euclidean argument. Therefore, you can't have negative energies in a path integral if the path integral is to exist. Therefore, something else had to happen to make it exist. Now, if you found that the path integral couldn't exist with any measure, then the theory is hopeless. So my view is the theory is hopeless if you cannot find a domain somewhere in the complex plane for which you can get a well-defined path integral.
Okay.
That's my starting point.
So
and that's
let's be clear
wait,
here. Are
Richard.
you-
So I think Zravan first has a comment.
Yeah. So I mean, you said like so your method is specific to. I mean, you're talking about only fourth order theory. Can you say your method of symplectic transformation in classical theory will not work for sixth order theory?
No, I just can't say anything because I've never looked at it.
I just want to point down, I mean, if like what is quantum gravity, you can go to sixth order, eighth order and everything, right? Only thing stops here is the ghost problem. But if it is solved, then any order theory is relatively good for quantum gravity, right?
I haven't said that because I haven't done a calculation, but I'm only interested in fourth order because it's the only dimension in which I get a dimensionless coupling constant and a renormalizable theory. So that's why I work in it.
But there are still additional terms.
I really don't know. I really don't know. But going back to what Richard said about minus lambda 5.4, the whole issue about determining the energy spectrum depends on boundary conditions, not on the structure of the Hamiltonian. It depends on the states that the Hamiltonian is acting on, and it depends on the boundary conditions. And what Carl did in his study of minus lambda 5.4 was he found a set of boundary conditions, and of course they're in the complex plane, for which the energy spectrum was bounded from below. So you can't even, maybe I can say it this way. If I give you a Hamiltonian, you can't even tell if it's Hermitian by looking at it. You can only tell if it's Hermitian if what it means is it's Hermitian when it acts on a specific set of states for which you can integrate by parts and throw away boundary terms, surface terms. But you don't know that until you construct the states. Another way of saying it is, let me say one more thing. If you write down a path integral, you have no way of knowing whether the quantum theory that you will produce will have a Hermitian Hamiltonian, because there's no reference to Hermitian in the path integral. And what I was able to show was that if the path integral measure is such, if it's real and the path integral exists on the real axis, then the quantum Hamiltonian is Hermitian. If you have to continue the measure into the complex plane, the quantum Hamiltonian will not be Hermitian, but it will be CPT symmetric. Okay, I'm sorry, that was just, so now you want to ask me something else, or ask something.
I'm saying, Richard has mentioned in your talk, you truncated the terms, right? You neglected these additional terms which come from anomaly, this while logarithm of box while. So, yes. Well, you said you are only interested in the terms which, I mean, okay. You have dimensionless coefficient, but you have additional terms as well.
Okay, I was trying to address a different question, but let me go back to what you've asked. I didn't want to say what the complete path integral is. I wanted to show that when I do the path integral, I pick up a fourth order derivative term. That's what I wanted to show. And therefore I said that if fourth order derivative theories give rise to ghosts, then the standard theory is no longer stable. Now you have two possibilities. Either the reasoning that led you to think there was a ghost in the fourth order theory is incorrect, which is the viewpoint that Carl and I have promoted, or these extra terms all organize themselves and cancel the ghost. But either way, you've solved the ghost problem. Unless the standard model before you did the path integral, unless it already had a ghost, which of course you'd be stuck with. But if the standard model doesn't have a ghost, then it must remain well behaved when it couples to gravity. And that's why I wanted to show you that this particular term appears. And therefore, if the standard model is to be stable under coupling to gravity, not whether gravity is stable when gravity is coupled to gravity. I was just asking whether the standard model is stable when coupled to gravity. And that's why I did this path integral. I generate this R mu nu minus a third R alpha squared effective Lagrangian. And as far as I can see, you have no choice. Either the fourth order theory is fine and the standard theory is fine, or the fourth order theory is bad news and the standard theory is unstable when it's coupled to gravity. I mean, I don't see any straightforward resolution of that other than the two options that I've just mentioned. And therefore, what I was trying to show in the talk, one second, Richard,
That's simply not true. What you're saying is false.
But you are
Richard, I don't
sorry,
mind
both of you. So I think we are in a loophole because you definitely disagree on what is important and what is not. And Richard is really interesting in what is the classical limit. Philip is instead talking about the Hamiltonian view. And so I think Luca now has a question.
Just to close this discussion, because of course, as you said, it's going a loophole. So just to rephrase, I think the claim of Philip. Okay, so it's true that the classical Lagrange that you have in the end is Weil anyway, Weil square. Okay, but there is any way. I mean, at least the claim I'm rephrasing. Okay, just to understand, because there was too much confusion. So it's true that the classical Lagrange that you have in the end is Weil square, but anyway, since you are starting from the quantum theory, you have anyway some remnant of your quantum prescription, which makes the ghost harmless. Is this what you're saying?
I'm saying exactly that. And I'm also saying that what we want to do in gravity is not recover Einstein gravity necessarily. I mean, nature doesn't require you ever to recover Einstein gravity. You only need to recover the solutions in the domain where they've been tested. What we want from a quantum gravity theory is to have it work exactly like QED, namely that you have a quantum theory, you quantize it, you construct matrix elements of the quantum operators, and they obey the classical equations, but with the dress charges. So if the theory is renormalizable, you can construct what's called a skeleton theory, and the only thing that you ever want to do from a quantum gravity theory is to have one for which the classical limit, and by that I mean the macroscopically occupied quantum operator matrix elements, obey the same equations. And that can only happen if the theory is renormalizable. Cannot happen otherwise. And that's why it's very difficult to construct a quantum theory of Einstein gravity, because you're working with a non-renormalizable theory. So you can have a quantum theory, but you have no way of knowing ahead of time that the matrix elements of that quantum theory are ever going to correspond to the Einstein equations. And that's why John Donahue and people try to treat Einstein as an effective theory, precisely for that reason. But my objective is to do for gravity what we've done for QED. And I don't think that we should be content with doing less. I mean, now, of course, you run into a problem if you want to finish up with the Einstein-Hilbert action, because you don't have a well-defined quantum theory. So that's, to me, an indication that you don't want to finish up with the Einstein-Hilbert action. But you do want to finish up with a classical theory that agrees with observation. And that's a whole different question.
Okay. So maybe
it's not a contour. Sorry.
That's the
sorry. Just to understand what you said, because to me it looks like that. Of course, I'm not saying that you should not go ahead and try to construct other approaches, but I mean, string theory is a clearly a counterexample to what you said, because string theory is not renormalizable. It's finite. I mean, at least in string perturbation theory. And in low energy limit, it gives Einstein gravity, obviously, because it gives massless graviton. So it just recovers the classical limit of low energy is Einstein gravity. So why are you putting this condition of renormalizability?
I'm sorry, I was referring to Einstein gravity in 4 dimensions. That was what I meant, not Einstein.
No, but even in 4, I mean, in string theory, you can.
I meant if I restrict myself to 4 space-time dimensions, namely to the ones for which there's evidence.
Okay.
That was anyway, all I'm saying is, it seems to me it's a very desirable objective to have quantum gravity work exactly the same way as quantum electrodynamics.
No, sure. That I don't have any problem with that. But what I don't understand, why should we restrict? Why should we restrict ourselves only with renormalizable theories? I don't see any reason for that. I mean, in fact, my talk was precisely the opposite to that. What I was trying to say is that renormalizability doesn't matter. Theory can classicalize in deep UV. And anyway, this is a small comment, sorry. Yeah.
Perhaps I can then answer your question, why do I even work in conformal gravity? Never mind the fact that it's renormalizable. Why do I work in it? I start out with the view that the universe, every particle is massless and all mass comes from the vacuum. Therefore, the massless theory, particles are propagating on the light cone, and whatever light cone symmetries the light cone has are the ones that you should require of the fundamental action.
No, I certainly admire that approach.
Light cone is conformal invariant, therefore I work in conformal gravity.
No, of course, I certainly admire your approach, and I think it's a fascinating question. But I'm just saying that I thought you made a statement that it only has to be renormalizable.
Okay. If something is conformal invariant, then it will have no scale in its coupling constant.
Okay. That's what you meant.
And it will be renormalizable. I didn't mean that was the starting point. The starting point is symmetries of the light cone.
All right, yes. I understand. Yeah. Sorry, Luca.
Yeah, sorry. Yeah, maybe I don't know. I think so we rephrased a bit all the things about Philip's approach, and I'm not saying that I agree, because maybe I should study better the paper to make some more things. But I think at least the claim now is clear. Okay, what you mentioned. So you don't have just classical bind, but you're saying you have some remnant from your quantum prescription, which anyway makes things harmless. Okay, cost harmless. So, but I have a question actually regarding Gia's talk. So maybe we can change a bit. So indeed, so far we mainly spoke about Wilsonian UV completion, because when we think about like R squared plus by square gravity, we are anyway having new degrees of freedom. Okay, we are trying to make the theory normalizable, but Gia spoke about something which is a bit different point of view. Okay, and actually you didn't mention it today explicitly, but in some of your past works you spoke about self-completion of general relativity. Okay, so I'm not sure I really understood the meaning of that, but is that basically your Einstein-Hilbert action is enough for UV completion of the gravitational interaction?
Well, okay, thanks for the question. So what I meant under self-completion is essentially what I tried to discuss today. So self-completion, the meaning I put there is the following. So you have certain theory which flows in deep IR to Einstein gravity, right? And now the question is, or to any theory, it doesn't matter. You have a theory which in deep IR flows to some theory, for some description. And now the question is whether deep IR knowledge of the theory is fully enough to recover a deep UV knowledge of the theory. Okay, this of course doesn't exclude that at intermediate scales you can have new degrees of freedom. These are perfectly fine. I mean, for example, string theory is an example of that. In string theory, which is a classicalizing theory, as I said, because string theory has black holes, and as long as theory has black holes, in deep UV, it will classicalize through black holes, because black holes will be produced because of what I tried to discuss. This is the self-completion is a statement about deep IR and deep UV behavior of the theory. So therefore, somehow what emerges is the following, that you have Einstein gravity at low energies, and no matter what happens at intermediate energies, this boundary condition that in deep IR we have Einstein gravity seems to control the deep UV outcome of Einstein gravity. So all these degrees of freedom that emerge at intermediate intermediate energies, they have to play along. So this is the statement. Now, so in other words, for example, even in pure Einstein, right? It would be totally silly if I say, oh, I have pure Einstein and I only have 1 degree of freedom, massless graviton. That doesn't make any sense. Why? Because even in pure Einstein, we have micro black holes. And micro black holes are just like particles, because if you have a black hole of the Planck mass, that is literally is indistinguishable from a quantum particle of the Planck mass, okay? So therefore, even in pure Einstein, it's not, the degrees of freedom are not only graviton, obviously they are degrees of freedom, but the statement is about deep IR and deep UV. So self-completion was, the statement was, and I think that's a correct statement. So from what we see so far, this statement seems to be correct, in the sense that it looks like that through the deep IR behavior, gravity sort of nails down its deep UV behavior. And in string theory, this is manifest. In string theory, you can even make it even further. It is through open-close correspondence and this kind of stuff. But what it looks like that this property is independent of what happens at intermediate energies. Okay. Now, of course, it could happen that the intermediate completions, they are highly restricted. That's most likely is true. So it could even be unique, maybe. I don't know. That's a separate question. But that's not what I'm addressing. I'm interested in deep UV behavior. Okay. Does this answer your question?
Yeah, no, basically, I was interested, let's say, in the role that, for instance, higher curvature term plays in your approach, okay? Because we know that basically we can generate R square term, Y square term very easily, even if we have some matter field coupled to
integrating out the
yeah. So I mean, of course, if you speak about your approach, you didn't consider any R square or Y square term.
No, it doesn't change anything in my approach. In ours, the beauty of this UVIR or this classicalization is that it is highly insensitive to higher derivative corrections. Because since we are talking about deep UV, since classicalizing theory in deep UV, the momentum transfer goes to zero, the high derivative contribution to the processes in deep UV are negligible. So they essentially they are 1 over n compared to the leading order contribution, and we're then going to infinity. They are just zero. Okay, so that's the power of it. That is completely, this classicalization property is completely insensitive to higher derivative, existence of high derivative. High derivatives, they may be needed there to improve behavior around the Planck scale. That's a different story. Okay, for example, if you want to do loop computations, string theory provides that. String perturbation theory gives possibility to do loop computations. So something like intermediate description that will take care of the issues around Planck scale or string scale or whatever. That is needed. That's a separate story. But what is important is that is not affecting the deep UV behavior of the theory. So it sort of stays only there. It's like in QCD. So in QCD, what do we have? At very low energies, right? Okay, we have theory of ions. Let's assume that quarks are massless, right? If quarks were massless, in a deep IR, I would have theory of ions. Now, in deep UV, I would have theory of gluons. Now, necessarily, there is one place where they meet, two descriptions meet, and they both become strongly coupled. So gluons are strongly coupled around QCD scale. Pions are also strongly coupled around QCD scale. That's unavoidable. So it is unavoidable that we hit strong coupling, and we have to live with it. I mean, in QCD, we're not making tragedy out of the fact that QCD is strongly coupled at around QCD scale. Why? Because we know that deep IR behavior is consistent, deep UV behavior is consistent, and there is no indication that around QCD, the strong coupling around QCD scale really violates unitarity non-perturbatively. So we try to use lattice and experimental data, etc. Now, it is perfectly okay if the same happens with gravity. So it's okay that if gravity hits some strong coupling, only at some limited scale. For example, around Planck scale. So imagine that around Planck scale, gravity behaves just like QCD behaves around QCD scale. So you have resonances, micro black holes. Technically, maybe very hard to compute those, but that's not a conceptual problem. So in that case, we may need to live with that. Now,
what if it never hits strong coupling at all?
Sorry?
These higher derivative theories are asymptotically free, many of them. What if it never hits strong coupling?
Different. No, that's different because those contain ghost degrees of freedom. That's the fundamental difference. So I'm not assuming any type of ghost-like degree of freedom or a degree of freedom that makes gravity asymptotically weak. This is, of course, this is fundamental.
So it is sensitive to higher derivative.
No. I mean, I'm assuming high derivative theory to contain infinite number of high derivatives, but do not contain any real propagating ghost degrees of freedom. Obviously, I'm making that assumption because I don't know how to deal with theories with ghosts. No, sure. No, thanks for
just to interrupt. What you are saying is absolutely correct. Nothing wrong, but it is true for any scale. It doesn't really matter. It should be true for even, say, nth derivative theory also. You can apply the same argument, what you have done.
No, so what do you mean? Which argument? Like I mean, what?
The argument of entropy, which you have floated. And
no, I'm not saying that. I'm not saying. Look, let me distinguish conceptual issues from technical issues. Now, I didn't study those derivative theories that may propagate ghost-like degrees of freedom. I'm simply saying I didn't study them. I'm not claiming that they are crazy. I see clear problems. I see clear potential problems in this description, and we were already discussing many of those. I see clear-cut problems there, but of course, I'm not making any theorem that necessarily this type of view completion is impossible. No, I'm only reporting what I'm thinking about. I'm saying I'm saying whatever theory is at the intermediate scales, like in string theory. So string theory is a very nice prototype model because in string theory, we have intermediate scales, we have intermediate excitations. We can integrate those out and we will get infinite series of high derivatives. But we don't have any physical propagating ghost in string theory. I mean, assuming we have critical strings. So that's my prototype. I'm saying this is the type of class of theories that I'm focusing on. And in those theories, what we are observing is that there is the deep IR, deep UV connection, and that's self-completion. So the deep IR knowledge of the theory already tells you in deep UV, everything is fine.
But that's what the point is. UV is always finite in string theory. The only problem is the infrared part.
It's not a question about finiteness. It's a question about whether IR theory captures UV theory. Of course, it's finite. I'm not talking about finiteness. Self-completion about the fact that theory through this saturon phenomena makes a bridge between deep IR and deep UV. And that's a highly non-trivial phenomena, okay? And so that is, of course, this is what I'm talking about. I'm not saying simply about finiteness, okay? And so therefore, for example, let's take example in string theory, obviously, for instance, when we compute in Einstein gravity, planetary orbits or compute emission of gravitational waves, we are not saying that in string theory this story will be any different. Why? Well, precisely because the strings at low energies, they decouple. So string theory in deep infrared flows to Einstein gravity. Now, non-trivial part is that even in deep UV, it flows to Einstein gravity because of these black holes, existence of the black holes in the theory. And that's the non-trivial part about self-completion. Yeah. I don't know if this answers the question.
No, it answers me. But I was saying that in principle, the argument which you floated could be applicable to even very highly excited states of strings as well. So
no, in string theory, that is manifest, because in string theory, there is no question. In string theory, highly excited string states are also classical. So string theory is a manifestly classicalizing theory from that point of view. Absolutely. So in string theory, these things are explicit. Now, the reason string theory is because it's a consistent theory. Since it's a consistent theory of gravity, it automatically takes care of this UV-IR correspondence of connection, okay? Yeah. But the question is that this thing seems to go beyond, and the question is, and the point is that it goes beyond gravity, and it goes beyond gravitational type theories. So there can be classicalizing theory, class of classicalizing theories can be much wider, okay?
Have you thought about, just a silly question, have you thought about applying this to Hagedorn phase? Maybe that would be interesting.
Well, a Hagedorn phase precisely has to do with high momentum transfer, above the string scale. And indeed, in Hagedorn phase, that's precisely the point. You excite very high excitations of strings, and that's why this Hagedorn phase takes care of this, yes. Yeah.
There is a comment by Bob.
Bob has a question, right?
Yes.
I don't know if it's to me.
You have to unmute yourself.
Oh, sorry. Yeah, are you saying that your picture is not consistent with an asymptotically free theory of gravity ignoring ghosts, just asymptotically free?
Well, in asymptotically free theory of gravity, if you have such a theory, of course, if someone manages to construct a consistent theory of gravity which is asymptotically free, of course, you could say, on one hand, you don't need classicalization anymore in that theory. Of course, you could say. However, the question will arise because if you have a theory which is asymptotically free, a gravity theory, but at the same time, it flows to Einstein at low energies, then the question is what you do with the interpretation of black holes. Because since you have black holes from the point of view of long distance observer, so now imagine that long distance observer is doing the following experiment. Takes the plus and minus, galactic energy or whatever, and collides them, and solar mass energy, let's say. Now, long distance observer, since long distance observer only sees Einstein gravity and is full control of IR theory, cannot have any other outcome. It has to form a black hole. Now, at the same time, you would say in deep UV theory, you have weakly interacting gravity, and so deep UV theory that doesn't need these black holes. Actually, they come as a bonus, but they are not needed for UV completion of the theory. So that would be the story there. So the story would be, if you have asymptotically free theory of gravity, which is consistent, of course, there is a big if there. I see many potential questions and many potential problems, also connected with ghosts, etc. But my answer would be that if you manage to construct asymptotically free theory of gravity, the black hole formation, classicalization there will be as an extra bonus. It will not be needed for UV completion, but it just will be there because black holes are there. Now, if you have some kind of theory of gravity which simply abolishes black holes, then of course it's a different story. So if you have a theory of gravity in which you modify, then I don't know, then it's a difference. I'm not discussing those types.
The question is whether we can see super Planckian gravitons or not.
Right, and this is connected with this question whether you can make gravity asymptotically free or asymptotically safe at short distances.
It seems possible to me, if you had such a theory, you would expect possibly to see super Planckian gravitons at scattering experiments.
Right,
and so you're not claiming to prove that couldn't happen, I guess.
No, how can I prove an unknown? I mean, I can only prove, I can only work within a framework and within well-defined assumptions. Now, however, there will be interesting behavior which would be reminiscent of QCD, because remember in QCD what happens, right? In QCD, of course, we do have gluons of very high momentum transfer, right? You can produce gluons of arbitrary. However, an asymptotic observer will never see those gluons. Asymptotic observer will only see hadrons as final states, because QCD will hadronize. So therefore, in such a theory, maybe black holes will play the same role.
We do see jets, though. So
of course, jets is different. Jets is there, but jets also have to do with the fact that quarks are sufficiently light, and so the QCD strings they break, etc. But no, sure. But jets are still multi-particle states. With jets, we see very highly energetic jets, but we don't see really gluons of high momentum transfer directly. Of course, we know they exist because we can compute things, and this is consistent. So therefore, if there is a theory of asymptotically free gravity, I would say that black holes would play the same role of hiding these very high momentum transfer gravitons as glue balls and hadrons play in QCD, something similar. That's what I would say. But of course, I mean, this is just hand-waving argument. As I said, I'm working within the assumption that the gravity is not becoming asymptotically free or anything like that. Yeah. But of course, yeah, we should keep thinking about all possibilities. I mean, I fully agree with that. Yeah.
Okay, so I think this is a good point to close the discussion. So I would like to thank again all of the speakers of the second session, even if two of them already had to leave. So thanks again to everybody, for the speakers and for everyone participating in the discussion.
Let's also thank Luke, Richard, and Alessia for leading discussions.
Yes, thank you very much.
Thank you.
I would just like to say that I've been going to many web conferences, but this is the first one that was a real discussion. I mean, I think the organizers have done terrific.
Yeah, actually, that was our main objective. Yeah, it seems that it's going well. Let's hope that.
As I said, it is the third pillar discussion. The fourth pillar is future. We will build. Hopefully, we will build. Yeah.
No, yeah, actually, I hope that all of you will try, to make an effort like today also in the next days, and we can repeat the same. So I think that the sunrise will arrive soon here in Japan. So here is 10 to 5, actually, yeah. So, but I think it's nice. Actually, even if we stay longer, for us, it's no problem. But yeah, I don't know if there is any other point this moment.
I think the success also lies with the speakers, because all of them have raised some thorny issues.
Yes, it's true.
Better to have thorny issues on the plate rather than just saying that everything is good and calm. So yeah, so today's discussion was good.
I guess we have to say to Luca and Straven, good morning.
Yeah, actually, yes.
also to Richard.
To Richard, yeah, actually.
Well, he's inspiring us to be awake. Yeah.
So yeah, I don't know if there is any other point to discuss at this moment, or we can
well, at this point, I just want to say today happens to be the Women's Day, so happy Women's Day to
sure.
Alessia. So
Thanks.
And Anna is also here. So Claudia.
Claudia left, unfortunately.
Yeah. Okay, so we can convey her the message. Yeah. Okay.
Thanks a lot.
Okay, so yeah, so I don't see any other point that has been raised. So yeah, I have to say sadly, yeah, see you tomorrow.
It's time. So
Okay, see you tomorrow.
Bye.
Bye bye.
Bye bye. Bye bye.